Alright, welcome to Lesson 11, our last video in this unit. It's titled Logistic Growth. So, let's review for a moment here. So what we learned a couple videos ago is that when the rate of change of a population is directly proportional to the size of the population grows exponentially. So what that means is, if we're talking about the rate of change of a population with respect to time, okay, that's directly proportional to the size of the population. So we have some constant k, right? We call that the constant of proportionality times our population, okay? And we said that when we solve this differential equation, we end up with an exponential equation, okay, of that form, okay? And so graphically, what's really happening here, if we were to look at a graph of p versus t, we have some initial amount, all right, and then it's growing exponentially. So the idea here is, if we were to look at the tangent line slopes, notice how the slopes in the beginning are not very big. So the rate of change in the beginning is not very big, and therefore the population is not very big. So that's the whole idea of it being in direct proportion to one another. However, as the rate of change gets bigger and bigger, so those slopes get greater and greater, notice how the population gets higher and higher in a proportional amount, okay? Now, this model is reasonable for short-term growth. However, if we look at growth over time, it's not very realistic. If you look at growth of certain populations, there's limiting factors that affect how much growth you have. Things like how much available food you have, the habitat, the amount of living space you have. Lots of different constraints that will impose limits on the growth of any real world population. So a more realistic model would look something like this. Okay, it's what we call a logistic growth model. So the idea here is it's going to start off, all right, and yeah, it might grow fairly quickly, but then it's going to level off. All right, so it's concave up, and then it turns and becomes concave down at some point. Okay, so let me do a little bit of a better job drawing this. So it is going up, concave up, and then it's going to level off, concave down. Okay, so after a while, you're not going to continue to see massive growth for your population. Okay, yeah, it may still increase, but it would be minimal, and you reach a point where it kind of reaches its maximum capacity. Okay, so this is what we mean by logistic growth. All right, it has a log in it. All right, so we can see that, you know, if you remember, a log equation kind of levels off. It grows very slowly. Initially, it's going to grow quickly, but then it's going to level off. Okay, so where it levels off, we give this a name. We call this the carrying capacity. All right, and we use an uppercase M to represent it. So think of it as like a room that has a maximum capacity, right? There's only so many people that are allowed in that room, okay? So it's the idea that if we're talking about population, our population approaches a maximal carrying capacity, okay? So it's only going to grow to a certain point, and then it's going to level off, okay? So here is the differential equation this time. It's going to be very similar to the one up above. All right, we're still going to have the k times the p, all right, that we see there. But then if we want this to level off here, then it's the idea of wanting to have a horizontal tangent line slope, or something that's going to be close to 0. So what we're going to do is we're going to multiply this by m minus p. So if m is your carrying capacity, all right, it's the total number of animals, where we're talking about people, okay, that we can physically fit in this environment, minus the current population. So if that is really, really close to 0, if m minus p, if you think of it as a limit that's approaching 0, okay, then that's going to cause this line to level off, because anything times 0 we know is 0. Now, if it's really close to 0, then our product will be really close to 0, okay? So this is the differential equation that we are going to be looking at for what we call logistic growth, okay? All right, so suppose we're looking at an example here where we're told the growth rate of a bear population in a certain wildlife preserve is modeled by this differential equation that we see. And notice how it fits the mold of what we just saw before. It has that additional factor of 100 minus p on the end. Okay. We are first asked to find the carrying capacity for bears. Well, this is really easy. You simply need to know that this portion of the formula is equal to the carrying capacity, which we call M. Okay. So this would simply be 100 bears. So what that means is after time, when this grows, we're really not going to see any growth beyond 100 bears. Okay, next part to this question is, what is the bear population when the population is growing the fastest? So again, recall that the general model here looks like this. And if we're trying to figure out where is it growing the fastest, that means we want to know where is its slope the steepest. Okay? Well, this is also very easy. You simply need to know that this is always going to be 1/2 the carrying capacity. Okay? So that is simply going to be 50 bears. So if you know that little mini formula, it's a piece of cake. Okay, and finally here, last question. We want to know, what is the rate of change of the population when it's growing the fastest? Well, we said it's growing the fastest at 50 bears. If we want the rate of change, we're going to use our derivative equation, okay, the differential equation that we're given. So we know that we have 0.008, that's the k, or the constant of proportionality. We know that the population at this moment in time, when it's growing the fastest, is 50, so that's going to go in for p. Alright, so we drop that in, we go straight to the calculator, and we're going to get 20, and remember it's a rate of change, so we're not going to say 20 bears, we're talking about 20 bears per year. Okay, so let's suppose we're talking about years for our unit of time. Okay, so the rate of change would be 20 bears per year. Okay, so if we're talking about a logistic growth differential equation, we're talking about an equation in this form here. All right, so now what we're going to do is we're going to look at a specific example where we have this differential equation and we're looking to solve it. And this is going to tie into our last video when we did partial fractions. All right, you'll see how that is going to be used in this process. I'm sure you're very excited. So given this differential equation here, keep in mind that our k value is 0.0003 and our carrying capacity m is 1,000. Okay, and p is going to represent our population. If we are asked to solve it, in the end we want p equals something. Okay, so to do this, just like any other differential equation, we need to separate our variables. Okay, so we're going to put this over 1, we're going to cross multiply. So we cross multiply and we notice that we have the p's over here on the side where we have our dt. So let's keep the 0.0003 on the same side as the dt, since that's just a constant. But then let's take this piece right here, this p times 1,000 minus p, and let's divide that over to the other side so that we have our p's on one side. So this is one big cluster of multiplication, so we can easily divide our terms over. So when we do that, this is what we're looking at. So we've now separated our variables. We have the p's on one side and then the t's on the other. Again, the number in front here is just a constant, so it doesn't really matter. So we'll keep that over there. Now, if we are going to integrate this, notice how we have a denominator that has two linear factors. So when you have a denominator that has two distinct linear factors like that, that needs to be your clue that you need to do that technique of partial fraction decomposition. So let's do that. Okay, so we're splitting this apart. We're taking the factor of p, putting that in the denominator on one side, and the other factor of 1,000 minus p, putting it on the other, and we have the a plus b as our numerators. So to solve, what we said was we're going to take this a, and we're going to multiply by the factor that's missing next to it. Okay. So that's 1,000 minus p plus the b is going to be multiplied by the other factor on the bottom, which is p, and that is going to equal our numerator from up above that we're changing it from. Okay. Now we said we need to look at where the fractions are undefined. So first we're going to use p equals 0 because that's where our first fraction is undefined. So if we were to plug in 0 for p, we're going to get 1000A is equal to, that would be 0 and then 1. Okay, so that would mean that A is 0.001. And likewise, if we use the other spot where it's undefined, which is P equals 1000, okay, we have 0 for the first term, then we'd have 1000 times B is equal to 1. We get the same thing, okay? So from there, what we're really looking to integrate is this. So we substitute in and carry over the right-hand side from before. So what we now have is 0.001 over P plus 0.001 over 1000 minus P. Okay, well, we see a lot of small numbers in here. It would be a lot easier if we multiplied all of these pieces by 1000 to give ourselves easier numbers to work with. So let's do that. Okay, so from there, we have a 1 over P plus a 1 over 1000 minus P dP. And on the other side, we'd have 0.3 left. Again, we just multiplied everything by 1000. So now we're going to finally integrate. So let's go ahead and do that. So we're going to have the natural log of P for the first one. And now the next one here, we're going to have another natural log, but the function on the inside is linear. And we would have to multiply by 1 over its derivative. The derivative is -1, so we'd be chaining along a -1. So let's just turn this into minus, okay? And then the natural log of 1000 minus P, we technically don't need to worry about absolute value here because P is the population, it's always going to be positive, okay? And then over here we would have equals 0.3T plus C. So now let's use a log property to condense this. Okay, so I just copied this over to give myself a little more room. I forgot to add something in the beginning. Let's suppose that we were given the initial condition that P of 0 is equal to 61. Okay, so our initial population here that we're starting with is 61. Okay, so we know that up front. So now we're going to use that to find C. So let's plug in and find our C. Okay, so when you do that, when you put in 0 for T and 61 for P, you end up with the natural log of 61 over 939, and let's just make it a decimal so it's less writing. Alright, so from there we know we're going to plug that in for C. Now if you just think ahead a little bit, if we look at this piece right here, we know we can condense it using a log property. That would give us P divided by 1000 minus P. Well, wouldn't it be nice if we can do 1000 minus P divided by P, because then we can divide that P into each of those pieces, alright, and one of the P's will cancel because P divided by P is just 1. So what I'm saying is let's negate these, let's go through and let's multiply all of our terms by -1 so that we can start with the natural log of 1000 minus P. So currently it's negative up here, so I'm going to multiply it by -1. Alright, so it becomes positive, and then I have a minus ln of P is equal to a minus 0.3T, and then I would end up with a positive 2.7339 for my C value. Again, I want to flip-flop these terms. You'll see why here, because now we're going to condense this. Okay, and then over here we're just going to copy this part over. Alright, and then we're going to drop an E underneath each side like this. So that's going to cancel. So now we have 1000 minus P over P is equal to, now remember your exponent rules, so negative 0.3T, and then this would be times E to the 2.7339. Okay, we can't drop an E underneath this as is and then just add them, right? You got to turn it into multiplication. Well, this right here is just going to be another number, and that number is 15.393. So let's clean this up. Okay, so again, the reason we flip-flop the order here is so that when we have P in the denominator, we're dividing each part by P, and then we see one of those P's disappear, and that's going to make it much easier to then solve for P. So let's add over our 1, and then finally to get our P alone, let's cross multiply. So after cross-multiplying and solving for p, we finally arrived at our solution. P equals what you see there. It's all in terms of t. Okay, so here again is our solution to this differential equation. Recall from earlier that we said that the K value is 0.0003 and the carrying capacity M was 1,000. Well, notice how the numerator here is M, and notice how this number between the negative and the T, this is really the M times the K, right? The 1,000 times that 0.0003. So if we generalize here, if this is our differential equation, then this is going to be the template of our solution. Now guys, the good news is you are not going to have to go through that entire laborious process of integrating like we just did. As long as you know that this is going to be the general form of our answer, all right, then you are good to go. It's just like with video number 10 where we talked about exponential growth and how that's going to lead to y equals y sub 0 e to the kt, right? We didn't have to go through that process every time. We knew it was going to fit a certain template, all right? So the M here is the carrying capacity. It shows up in a couple different spots. The K is our growth constant, okay? So the hardest part is just determining what A is. So you're not, again, going to have to go through this whole process like we just did. Instead, keep in mind you're going to be given some sort of an initial condition. That is going to give us a value for T and for P. And we know that from the original problem, we're going to be given our K. That shows up in our differential equation. Okay, so we would be able to solve for our A, and we'll also know M, right, from the original differential equation. So we will have all of these variables except for A, so that'll allow us to solve for A and then substitute back in. Okay, so sorry for the long video. I did the best I could. Okay, good night. Bye-bye.